In this video, we're going to see some additional examples of finite-state machines. We'll also talk a little bit more about how finite-state machines work. Let's begin with a little terminology. We use the word accept or recognize to describe the languages of finite-state machines. So we might say the language that some machine M accepts is A, for example. Or we might also say the language of M to refer to A. We can also use the term recognize as well as accepts. And to be precise and most accurate, we really ought to say that the machine recognizes a language and it accepts strings in that language, although we oftentimes say that a particular machine accepts a language. It really truly recognizes the language and either accepts or does not accept individual strings in the language. One string that's always of interest and somewhat confusing is the empty string. It has 0 length and it consists of no symbols at all, a sequence of 0 length. And it's represented by the symbol epsilon, which I draw like this, but which is often shown like this. This is the Greek letter epsilon. And a finite state machine that accepts or recognizes, that accepts the empty string is going to look a little bit like this. The initial state is also a final state. So here's our little arrow from nowhere indicating that Q0 is an initial state, but we also see the double circles indicating that Q0 is a final state as well. So we're immediately there. So if the string has 0 length, when we begin we're in the initial state, and immediately we're done and we find ourselves in a final state. So in that case, the empty string is said to be accepted by the finite state machine. We can also talk about something that's quite different, which is the empty language. Remember, a language is a set of strings, and there's always the case of the empty set, which can be symbolized using either the double braces or this 0 with a bar through it. And in that case, what the finite state machine is going to look like will be one in which there is no pathway, no way to reach a final state from the initial state. So no string can get from the initial state to a final state. It's oftentimes easy to confuse the empty string, epsilon, and the empty language. And it's important to note that these are not the same. Okay, the empty string is not the empty language. And a language containing the empty string is not an empty language. It has one element. It's a small and rather uninteresting language, and the only string it contains is the empty string, and that string has no symbols in it. But nonetheless, there is a string there, and that string makes that set not empty, so it is not the same as the empty language. So we say that if a machine accepts no strings at all, then it recognizes the empty language. In our next example, we want to build a finite state machine that recognizes a language. So we'll start by saying that our alphabet, sigma, consists of just the characters 0 and 1. And the language that we want to recognize with this finite state machine will be one that contains any string that does not contain the sequence 0011 in it. And we might say, well, gee, how do we begin to design something like that? And one approach to designing anything, if you're having troubles getting started, is to try a simpler problem. Okay? And so what's a simpler problem in this case? Well, a string that does contain 0011 might be somehow related, so that might be a fruitful way to start. So we might be able to solve that problem, and in solving that problem, we might be able to make some headway or progress on our larger problem, our real problem. So let's think about that. Here's a solution, and let's work through it. Let's look through it and see how it works. First of all, it's a finite state machine with an initial state, and again, in this example, we have just a single final state. And notice there's a pathway of transitions that are marked 0, 0, 1, 1 that will get us from the initial state to the final state. So certainly this thing recognizes the string 0011. Now let's look at the other transitions. This is a deterministic machine, and at every state there are two edges leaving. So there's a 0 and a 1, 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 and a 0 and a 1 from every state. By the way, this notation here represents two separate edges. One is labeled 0 and one is labeled 1, although to save space we oftentimes just use a comma to indicate multiple edges like this. So if this thing starts with a 1, well, we kind of stay in the initial state until we get that first 0. But then if we get a 1, we go back because we haven't seen the pattern 0, 0. And so this state right here indicates that we've seen a single 0, but whatever preceded the 0 was a 1. Okay? Whether we got there this way or whether we got to the initial state this way, we can only get to the initial state if there was not a previous 0. So this is the first 0 by itself. And then this state here represents the fact that we've seen two zeros in a row. The only way we can get to this state is by seeing two zeros. If we see 3 or 4 or 5 zeros, then we've seen two zeros in a row. So we're on our way to seeing and detecting the pattern 0011. But we still need two 1s. Now if we get a 1 after a bunch of zeros, then we're almost there. We've got 001. And so we move to this state. And if we get another 0, then oh darn it, we don't have that pattern. And so we have now seen a 0, but it's a single 0 by itself. So we go back to this state. Okay. And then maybe if we see a second 0 again, we could get back here. On the other hand, if we see a 001, then we're in this state. And if we see that last one, we can move to the final state. We've detected that string that we're looking for, and now we just pick up any remaining symbols following that pattern, staying in the final state. So this is a machine that solves the problem of recognizing a language that has 0011 in every string. But our goal, remember, was to recognize the language that contains strings that do not contain 0011 in them. So if you think about it, we just want the very opposite language. So what we can do, and here's our solution, what we can do is just flip the states from being final to being not final, or from being not a final state to being final. So now we have 4 final states. Okay? And you can imagine going through this machine the same way we went through M1, and up in these states we haven't yet detected the pattern, but the minute we detect that pattern we end up in this state, and nothing we can do can get us out of this state. So we reject. But as long as we can proceed through our string and not find the pattern 0011, we'll stay in one of these 4 final states. But the minute we detect the pattern, we enter this last state, and from here we can never get out, so we will reject that string when we get to the end of it. Let me say again what I said earlier about terminology. We want to say in particular that a finite state machine accepts a string, and it recognizes a language. And we can use this notation, L parenthesis, M parenthesis, where M is the machine that we're interested in, to indicate the language that that machine recognizes. So in our previous example that we just got done with, the language of M1 was the set of strings over the alphabet 01. Okay, so this star indicates all the strings we can form, all the finite length strings we can form from the characters 0 and 1. So the set of all of those that contain 0011 as a substring. And the language of M2 was the set of strings over 0 and 1 that do not contain 0011. And we got to this by complementing a language. So it's interesting to notice that these two languages are the opposite. They're complements. Of course, we have to have a universe in order for the concept of complement to make sense. And in our case, the universe is all possible strings made of symbols from the alphabet. In our case, sigma, the alphabet, is 0 and 1. So our universe is the set of all strings that you can make, all finite length strings you can make with zeros and ones. And when we take complements of sets, it's always relative to some universe. Oftentimes the universe is implicit. We don't really have to say what it is, or we don't say what it is. But it's always important to remember that there is a universe, and the complement is relative to that universe. And so the language of M1 is the complement of the language of M2. And likewise, the language of M2 is the complement of the language of M1. Let's practice a little bit. Here's the finite state machine with two final states. What language does this thing recognize? Well, let's see. If we start here, we see a 1 and a 0. So it recognizes the string 1, 0. And what about if we go this direction? Well, we see a 0, possibly followed by some more zeros, followed by a single 1. So it recognizes 1, 0 and 0, 1, 0, 0, 1, 0, 0, 0, 1. In fact, we can use this notation, 0 plus 1, to indicate these kinds of strings. This plus means one or more occurrences. Remember that star means 0 or more occurrences. When we see a plus as a superscript, it means one or more occurrences. So we can write this language down in set notation, and we might write it this way. L is the set of strings W, where W is either 1, 0 or a string of at least 1, 0 followed by a single 1. But now I want to ask, what about these strings? 1, 1, 1 or 1, 0, 1, 0. What happens in our machine here? Well, let's try 1, 1, 1. We go here, and oops, wait a minute, there's no place to go on the second 1. Likewise, 1, 0, 1, 0 would lead us to here, and then from here, where do we go? There's no edge. So really, this finite state machine is not completely specified. It doesn't seem correct. Remember, we said that the transition function was a function. From every state, there should be an edge labeled 0 and an edge labeled 1. But we don't see those here. So what's going on? Is this thing altogether illegal or what? And the answer is, it's not illegal. It's just a form of shorthand. So here's a similar finite state machine, and this time we've added all the missing edges. We've also added a new state, which I've labeled dead here. And this is a very common technique for finite state machines, where you have a single dead state, and any missing edges, if you will, go to the dead state. And once you're in the dead state, you stay in the dead state. So this machine now accepts, or now can process a string like 1, 1, 1. It leaves you in the dead state. Or a string like 1, 0, 1, 0. Again, these strings are now handled properly. So from here on out, we're going to assume that every finite state machine has a dead state, and any missing edges that aren't shown in the finite state machine will go to the dead state. So delta is our transition function, and formally it must be defined for every state and for every edge. So if some transitions are missing from our diagrams, we'll just assume there's also a dead state that we didn't bother writing down. So we prefer not to show the dead state, but we'll assume that it's there, and any missing edges that aren't shown in our diagram go to this dead state, and once you're in the dead state, you stay in the dead state with edges that are labeled with all of the symbols from your alphabet. Now we're in a position to give a formal definition of what computation by a finite state machine is. So let's assume that we've got a finite state machine. We'll call it M. So of course it's got states and transition function and so on. And let's assume we've got a string. We'll call it W, but it consists of a sequence of symbols from our alphabet. Okay, a finite sequence of symbols from our alphabet sigma. We can say that the machine accepts this string if there's a sequence of states that we can go through in our finite state machine that begins with the initial state. So here we're saying R0 is the initial state, and ends in a final state. So here we're saying that Rn is one of the final states. And furthermore, that every state is connected to the next state with an edge that's labeled by the corresponding symbol in the string. Here's the way we say that formally. For every state in this sequence of states, such as R sub I, we can get to the next one through our transition function, delta. Okay, we can get to R sub I plus 1 because there's an edge in our transition function from R sub I that's labeled with the corresponding symbol in the string. Okay, so this is basically just saying that M, the machine, accepts a string if there is any path, any sequence of states that will work. We've got to start in the initial state, we've got to follow edges legally, and this is how we say that, and we've got to end in the final state. And once we know what it means to accept a string, we can define what it means for a machine to recognize a language. So here's our formal definition. A machine recognizes a language if that language is the set consisting of strings that that machine accepts. So the set of all strings that machine M accepts forms a set, and that set is the language that M recognizes. Now we're in a position to define what is a regular language. A language is said to be a regular language if and only if there is some finite state machine that recognizes it. So if there's a finite state machine that recognizes the language, then the language is regular. Likewise, if the language is regular, then by definition there must be some finite state machine that will recognize it. It's important to have kind of an intuitive notion of what regular languages are. And we can ask, what languages are not regular? And the answer has to do with memory, I think. In the finite state machine, as you are looking at the string, there's a little bit of memory, and that memory is contained in the information of what state you're in. So if you're going through a finite state machine looking at a string, you're in some state. And that's the only memory you have. And in particular, you can't back up and look at an earlier part of the string to see if it matches or do some computation on it. And the amount of memory you have about what has occurred before a particular point in a string is limited to however many states you have. You can't store the string. You don't know what's happened before. You just know what state you're in. You can't count. A language that requires some sort of counting is not allowed. So I have some examples that are not regular. So just to give you an idea, these are some very simple languages. You could easily write a computer program to recognize any string in these two languages, but they are not regular. So here's the first one. I've indicated the language by WW, where W is a string of zeros and ones. So the idea is you have, every string is made of two parts, the first part and the second part, and they are identical. So here's an example string in the language, 01101, 01101. Okay? The first half is equal to the second half. And the reason this is not regular is because in order to check this part, you've got to remember what you've seen before, and this can require an arbitrary amount of memory. The first half can be arbitrarily long. So a finite number of states is not enough to remember everything you've seen, because that is not limited, it's not bounded. And here's another one that requires counting. again, very simple to write a computer program to recognize this language. It consists of a set of strings where you have a number of zeros followed by the same number of ones. Here's an example with 6 zeros and 6 ones. To recognize this language, you just scan the zeros and count them. And then you scan the ones and count them. And you see if those two numbers are the same. But this is beyond the ability of a finite state machine because finite machines can't count. The finite state machine is very limited, and anything that requires memory is not regular. So another way to look at this might be to imagine that you are a finite state machine and you're trying to recognize a string. But it might help to imagine a really, really long string. So imagine a string of characters that goes from here all the way out to the moon. So this is the Earth, there's the moon, and our string has millions, billions of characters in it. Okay? And you're trying to recognize and tell me whether that string is in the language or not. And here you are, you're looking at some character out of the millions or billions in this string, and you see an A, okay? And you know what state you're in. I mean, you have just a finite number of bits to represent that state. For example, if you have a finite state machine with 8 states in it, you could represent the state with 3 bits. So you have a small number of bits of information, but you have a huge amount of characters that have gone by up until before you reach this point. So can you recognize this string? Well, if it's a regular language, you can sort of ignore or summarize everything you've seen so far with that small number of bits. That is, you can remember anything you need to remember from the past, from the previous first billion characters, by the simple information of what state you're in at that point. So this is the kind of limited ability that finite state machines have. Even though finite state machines have a very limited ability, they can still do some remarkably interesting things. So in this next example, we're going to look at a language that it turns out is regular. And you might not at first think it's regular because it appears to have a need to do counting or arithmetic in order to answer the question of whether something is in the language or not. So the language I'm interested in is the set of binary numbers that are divisible by 3. So we're going to use an alphabet of zeros and ones. And here is the language. Okay, there's a binary representation for 0, for 3, for 6, for 9, for 12, and so on. And is this language regular? Well, it turns out it is. And we can see that by sort of asking what happens as we scan each number. What does it do to the value of the number? So imagine that we've scanned some long binary number, and I have no idea what value that is. 10110101011000001. Who knows what value it is? It's some value though. Okay, and we scan the next bit in the sequence as we're on our way to the moon here, trying to figure out whether this number is divisible by 3 or not. And it can either be a 0 or a 1. And we can ask, what does that bit do to this value? Well, if it's a 0, as you probably know, it has the effect of multiplying that number by 2. And if it's a 1, again, we shift the number over, which is equivalent to multiplying it by 2, and then we add in a 1. So these are the operations that the next bit will do to that number. Now, let's look at what it means to be divisible by 3. Well, it means the number can be written in the form of 3x. And if it's not divisible by 3, then the number can either be written in the form of 3x plus 1 or 3x plus 2, where x is an integer. So now, let's ask assuming we know whether the number so far is divisible by 3 or not, let's ask what the next digit does to it. Okay, so this is a bit tricky, but here in red are the possible kinds of numbers that we might have. We might have up till now seen something that is divisible by 3, or we might have seen something that's not divisible by 3, but has a remainder of 1, or possibly 2. And if we see a 0, what we're going to do is we're going to multiply it by 2. That's what happens if we see the next 0. So now the value of our number will be 2 times 3x, if it was divisible by 3. And we can rewrite that arithmetically and see that it's 3 times something that's an integer. So again, we can see, since we can put it into this form, that it is divisible by 3. What if we see a 0 for something that was divisible by 3 with a remainder of 1? Well, we multiply that by 2. Arithmetically, that turns out to be 3 times an integer plus 2. So it's still not divisible by 3. It's divisible by 3 with a remainder of 2. And if we saw something that was divisible with a remainder of 2, then we multiply it by 2. We find that that's equivalent to something that is 3 times an integer plus 1. So now it's divisible by 3 with a remainder of 1. So now let's look at what happens if we see not a 0 but a 1 instead. So again, we're going to look at our 3 cases. If we see a number that's already divisible by 3 and we see a 1, then what we're doing is we are multiplying by 2 and adding 1. Arithmetically, we can rewrite that this way. And we see that we have something that's now a multiple of 3 plus 1. So it's still not divisible by 3. What if it was divisible by 3 with a remainder of 1? Well, then if we see a 1, it's equivalent to multiplying it by 2 and adding 1. And if we rearrange that, we see that it's the same as 3 times 2x plus 1. So it's 3 times something that is now an integer with 0 remainder. So if we see a 1, it becomes divisible by 3. And finally, if it's divisible with a remainder of 2 and we see a 1, then we find out the resulting number is divisible by 3 with a remainder of 2. So we've got these 3 states indicating divisible by 3, or divisible by 3 with a remainder of 1, or divisible by 3 with a remainder of 2. And we can put those together into our finite state machine. And here it is. It takes us 3 states, and we've got the first state being that we've got a remainder of 0. Okay, so that's this state. If we see a 0, we stay divisible by 3, so we'll put a 0 here. Here is the state that corresponds to having a remainder of 1, and if we see a 0, we go to the state that indicates that it's a remainder of 2. So we label this with a 0. And then if we're in the state that indicates it's divisible by 3 with a remainder of 2, and we see a 0, then it indicates it's divisible by 3 with a remainder of 1. So we go back to this state. Okay. Now the other state should be labeled with 1, but let's just go through and check. If we're in this state and we see a 1, we go to this state, so that's correct. If we're in the state where it's divisible with a remainder of 1 and we see a 1, then we go to the state where it's divisible by 3 evenly. So there. And finally, if we're in the state where it's divisible with a remainder of 2 and we see a 1, we go to the state where it's divisible by 3 with a remainder of 2. So we stay in the same state. So now we've labeled the edges.